Hello all, let us discuss problem number 3 for wind load calculations. Now, in previous 3-4 videos, we have understood how to calculate wind load for multi-story buildings. Now, we are going to understand how to calculate wind load for water tank. Let us see this interesting topic. Here, problem 3 is like this. Estimate the wind load for a water tank for the data given. Total height of the tank is 27 meter, which includes height of supporting shaft 20 meter, height of bottom conical portion which is 2 meter, height of cylindrical portion which is 4 meter, height of top dome which is 1 meter, diameter of supporting staff or shaft that is 4 meter, and diameter of cylindrical portion is given as 10 meter. Location of water tank is in Ahmedabad. Terrain category is 2. Terrain class is also given as class B, but in IS 875 part 3 2015 version there is nothing required as class A, B, C, D or anything. So only terrain category is enough. Ground slope is 1 vertical to 7 horizontal, 1 chin 7 or 1 to 7 we can say. Hill height is 280 meter. Location from crest is given as 100 meter windward, and design life of the building is 100 years. Let us see further. Here it is a graphical representation of the water tank. Here we can see top spherical dome is having height 1 meter. Now the cylindrical portion is having height 4 meter. This conical portion is having height 2 meter, and the shaft which is supporting the tank is 20 meter height, and this is a ground line. If we talk about diameter of the supporting shaft is 4 meter and diameter of the cylindrical portion is 10 meter. Now let us understand how to solve the problem. Here we will do the same way we have solved previous two problems, step 1 and 2, VZ and PZ. But some methods, some techniques to get VZ and PZ will be changed here according to the structure, as it is a water tank. Let us see first thing, design wind load, which is VZ or we can say VB, which needs 5 things: VB, K1, K2, K3 and K4 according to page number 5 IS. Now for VB, we will find out VB in appendix A, page number 51. There is a table given for all the popular locations, popular cities. The wind speed, basic wind speed is given, and according to that, Ahmedabad is having VB as 39 meter per second. K1 is probability factor, risk coefficient. Table number 1 will provide the data. For that, here design life is 100 years given, and basic wind speed is also known as 39 for Ahmedabad. So 1.06 will be the value for K1 according to table number 1, page number 7 in the IS code. Let us move to the next item, which is K2. For K2, we will take table number 2. Table number 2 is given on page number 8. Now, according to height, we take table number 2, right? Here, total height of the water tank is only up to 27 meter. So, we will take height 10 meter, 15 meter, 20 meter and 27 meter only. Now for 10 meter and terrain number 2, terrain category number 2, 10 meter the value is 1, then value is 1.05, 1.07, and for 27 we have to interpolate between 20 meter and 30 meter. and it comes out as 1.105. So I have a small table prepared for K2 for the problem. Now for K3, which is a topography vector, I have to do some different technique. I have to use some different technique for this water tank problem. Please give your attention here. It is most important part and new part of this problem. Now, slope is given 1v to 7h, 1 vertical, 7 horizontal. So I can get my theta from that. And tan theta will be v by h, 1 by 7. So I am getting theta as 8.13 degree, which is greater than 3. And whenever theta is greater than 3, IAS code suggests that you have to see appendix number C, and you have to differently calculate K3 rather than taking 1. So for K3 here, I will use appendix C. K3 is equal to 1 plus C into S0. Now theta is in between 3 and 17. So LE effective length will be same as our length, and page number 54 should be referred for that. Here I have a crest. The distance from crest is also given as 100 meter, as well as height of the structure, sorry, height of the crest is also given as 280 meter. Now I can find out C from Z by LE into 1.2, as I am having theta. Again I will calculate same way I was calculating in the previous problems. Let us see. Tan theta is equal to Z by L. Here Z is given, L is should be find out. So I will get tan theta is equal to Z by L. I will make L as a subject of the equation. I will get L value as 1960 meter. Now I know L, I know X. So I will find out the H value from here. For H value, I will do what? Tan theta is equal to H, which is unknown, by L minus X. So I will get my H, and according to that, H is equal to 265.71 meter. So now I have H and L. So H by L, H and L will help me to find out C and S0. For C, Z and L are required. So C is equal to 1.2 into Z by LE. So Z is 280 and LE are found at that 1960. So C will be 0.171, and for S0, I will need H by LE and X by LE as usual. So H by LE, that is 265.71 by LE, and X by LE 100 by 1960. So both are lesser than 1. So, and one more thing, we have assumed here it is in a downwind slope as greater than 3, and we can refer figure number 13b, hill and ridge. Now S should be found out from H by LE and X by LE, as our previous problem suggests. Now, so here in the question it is given that the structure is it is on windward side. So we will take these, and figure 14 will lead us to S0 value or S value. Here x by LE is 0.05. So it is 0.5. So it will be very less than 0.05. So it will be somewhere here. And H by LA is 0.13. So again it will be a very less value. So here it is a zero point 0.8 value. So it will be lesser than that. So we are taking S0 as 0.7 again. As S is 0.7 and I am having C value as 0.171, K3 will be found out that 1 plus C into S0, 1.1197, and it is rounded up to 1.12. Now I am having K3 value also. After K3, I will move to K4. K4 is very simple, page number 8 and 9 of IS code, clause number 6.3.4. There are three values, but generally it is taken as K4 as 1.0 for all other structures than the cyclone important structures or industrial structures. So let us move to next thing, that is KD, KA and KC. So to find out KD, here we follow page 9 and 10, clause number 7.2.1. You have to give your attention here. Let us see KD. KD is taken as 1 here because KD is what? Wind directionality factor. Now, wind directionality factor, when the structure is nearly circular or circular, it is told that KD should be taken as 1.0. So KD is 1. Now for KC is a combination factor. So combination factor here, in a water tank case, there might be a structural collapse and it might harm to the people. It might be hazardous to the people. So for the safety reasons, whenever you are having circular or nearly circular form, you should take combination factors as 1. It should be only reduced when you are taking wind loads on frames or having a clad buildings or having different patches of the buildings which are square or rectangular. So it should be reduced in that case only. So generally in circular or nearly circular form, Kc should not be reduced to 2.9 and it should be taken as 1.0. Keep this in your mind. Next thing, that is Ka, area averaging factor. Generally in framed buildings or framework having building or trussed towers, we do take area averaging factors according to the frame tributary areas, right? But in this case, you cannot take that and you have to go safe for the design, and for safety reasons, you will take Ka as 1, assuming tributary area will be very less, which will be lesser than 10. Generally, this factor depends upon tributary area. How? If the tributary area is large, then the pressure coming to the building will be lesser. If the tributary area is very less, if you open the window very less, the wind pressure will be much more than when you open the window more. Like it works like that. So here, for safety reasons, Ka will be taken as 1. Now Kd into Ka into Kc will be obviously 1 and it is greater than 7. It is a typing mistake, but it should be greater than 7. It should be minimum zero point 0.7. So it is okay. Now we will move to our basic table. You understand now what is hill and ridge and what is cliff and escarpment. Let me give you the brief. When the structure is on a 3D type of mountain or 3D, three-dimensional mountain, it is known as hill and ridge. If it is in 2 dimensions only, it is known as cliff or escarpment. Now we will prepare the table. Here in this table, height will be varied 10, 15, 20 and 27 because our top height is 27 only. Now VB will be constant throughout all these heights, that is 39 for Ahmedabad. K1 will be constant, K2 will change according to previously prepared table. K3 will be same, K4 will be same. From that, Vz or Vd will be got. Now, how to get Vz? For that, we will multiply column number 2, 3, 4, 5 and 6. These columns will be multiplied as Vb into K1 into K2 into K3 into K4, and we will have these values. According to heights, these values are different. Same way, Pz can be get zero point 0.6 into Vz square. So it will be a different value for all these stories obviously, and from that as well as KdKa into Kc value, which is 1, 1 and 1, we will get Pd. Here Kd into K into Kc is 1.0. So it will not change. So it will be the same as Pz. So that's it. Step 1 and step 2 are over here, in which we found out VZ, PZ and PD. Let us move to the next step of this problem, that is step number 3, wind force calculation. For water tanks or any structure retaining aqueous things or liquid kind of materials, we have to calculate with Reynolds number. What is that? Let us see. Here there is a graph, figure number 5, which is given in reference of page number 56 of IS 875 part 3 2015. In that, CF would be found out through this graph. This graph is what? Let us see that. It is RE, Reynolds number, versus CF upon 1 plus 2 epsilon by D. Now, these quantities are somewhat different in terms of when you are retaining some different chemicals and all. But in water tanks, we have to keep it simple, so that we will assume one thing: epsilon by d is equal to 0.001. So if epsilon by d is 0.001, we can write down epsilon by d is equal to 1 into 10 raised to minus 3. So here the graph values or lines for CF, drag coefficient CF, are given in terms of epsilon by d into 10 raised to 3. So we are assuming it like that. So epsilon by d into 10 raised to 3 will be 1. So we are assuming that it is on the line for epsilon by d into 10 raised to 3 1. So on this line. So the values for CF will be on this line only. We are assuming this. Now, how to calculate RE, Reynolds number? If we put one value and two values, then and then we can get CF. Na? So, we have to find out RE value. For RE value, there is a formula given on page number 56, D into VD upon gamma. Now, gamma should be taken as 1.46 into 10 raised to minus 5. It is also mentioned on page number 56. Now, what to take D and VD? Here, D is to be taken as 10. The diameter is of 10, and VD is coming from pressure at top. VD is designed velocity at top, 51.16. Now, Reynolds number is 3.5 into 10 raised to 7. Now, I have RE, I have this line. Now, only thing remaining is C upon 1 plus 2 epsilon upon D. For that, I will put these graph on line 1, that is 1.0, and RE value of this graph, RE value which was found out 3.5 into 10 raised to 7. So 3.5 will be 3 and 4, in between 3 and 4. So it will be, the value will be like this. So if the point is here, the value will be simply zero point 0.9 or so. So I have assumed as 0.92. CF is equal to 0.92 into 1 plus 2 epsilon by d. Epsilon by d is assumed as 0.001. So I am putting all the values and I am getting CF. CF as 0.92. Now my drag coefficient is 0.92. If I am having drag coefficient CF, I have to still multiply it with K, which is given on page number 40, to get correct CF or modified CF. For that, I have to need to calculate K. For that, table number 28 is referred. For that, you can also refer the clause 7.4.2.2 that says you have to multiply CF with K, which is a reduction factor basically. Now, for K, I will need two things: which kind of flow is there and what is the ratio of I by D. or we can, sorry, ratio of L by D. So first of all, flow will be 6 meter square per second. If it is lesser than that, there will be a different flow. If it is greater than that, there will be a different flow. So I have to check diameter of that. So diameter into VD. So diameter 10 into VD, that is 51.16. It is coming out as 511.6, which is obviously greater than 6 meter square per second. So diameter is greater than that. So it is a supercritical flow. The wind will flow in a supercritical manner, which has already been studied. Supercritical flow and subcritical flow is already been studied in fluid mechanics, right? It is kind of there. So for that, I will take it is in between the range of these and these or these and this. So for that, I will need L by D. L by D is coming out as 27, which is length, and diameter is 10, so 2.7. So L by D is coming in between both of them. So I have to interpolate. But here for value of 2 it is 0.80 and value of 5 is also 0.80. So 2.7 will be obviously K will be 0.80. So I got my K value, which is a reduction factor, is 0.8. So CF into 0.8 will give me 0.736. It is a final CF. I can take it into calculation now this CF. Now I will calculate areas because CF PD is there. Now I will need AE. For that, as per calculation, I will find out AE. For supporting shaft, I will start it from bottom. Supporting shaft 20 is the height and 4 is the width or diameter. So 20 into 4 it is 80 meter square. Conical portion is like this. So A plus B, it will be considered as a trapezoid, right? So A plus B by 2 into H. So A is this, B is this. So 4 plus 10 by 2 into H. H is 2. So 14 meter square. Third area, cylindrical portion, this area 4 into 10, that is 40 meter square. Top dome, this area will be calculated as base into height by 2. It is approximate. So top dome area is 5 meter square. So I have 4 areas of different 4 components. Let us see how to calculate wind pressure, wind force and moment. So in this table, serial number, so 4 components are taken. Components, supporting shaft, conical portion, cylindrical portion, top dome. 4 things are taken, which is quite clear. Third column is for force in kilonewton, distance and moment. So for water tanks, these are the only things are to be found out. Let us see what are the components, what are its range. So supporting shaft is starting from 0 to 20 meter. It is in the range of this. Conical portion is in the range of 20 to 22 meter from ground. 20 to 22, right? Cylindrical portion, this portion is in the range of 22 to 26 meter, and top dome is 26 to 27 meter. It is quite clear. Now, what are these calculations? So, for finding out force, I have to multiply CF into AE into PD. Now, CF, that is 0.736, area we calculated in the previous slide. So, CF will be common in all 4 components, which is 0.736, 0.736, 0.736, 0.736. E will change. How? All the components are having different areas. In previous slide, we took AE for supporting shaft as 80, 80, 14, 40 and 5. 80, 14, 40 and 5. So CF and AE are quite clear. Now PD. PD for different heights. Now PD for, I will need PD for 0 to 20 meter. So maximum pressure will be at 20 meter. So I will take the value of PD. from our previously prepared table, which is after step 1 and 2. Here, yes, PD I will take it from here. For 20 meter it will be 1472.53. But in kilonewton per meter square it will be 1.47, right? So for 20 meter height I am taking PD as 1.47 in kilonewton per meter square. Now for ranging height up to 22 meter, I have to interpolate between 20 and 25. So PD will be 1.550. Again, for height 26 meter, I have to interpolate between 25 and 27. So it will be 1.56. And for last PD, for 27 meter, we have calculated already, that is 1.57. Let us see it again. In this table, PD for 27 meter height is 1.57 if we calculated it in kilonewton per meter square. So that's it. CF, AE and PD are there. CF, AE and PD are there, and you are quite clear about all of three. So forces are like that. The multiplication answer is 86.55, 15.46, 45.93 and 5.78. These are all forces. Now these all forces will apply some moment on the structure. Different forces, different distance, different moments. Let us check that. So force is 86.55, but it will be applied on its CG. So supporting shaft is like this. It's CG. Supporting shaft CG. Item 1 CG will be where? At half of the height. So half of the height is shown by this blue arrowed line, two-side arrowed line. It is showing 10 meter, so it is 10 meter distance. So force is 86.55, 10 meter is the distance, so 865.5 is movement for supporting shaft. Another distance, if we talk about distance at second component, it will be the red arrowed line. It will be 20 plus half of 2, that is 21. So force into 21 will give me the moment. Again, for third component, cylindrical portion. This cylindrical portion is having CG height as 20 plus 2, 22, and half of this. So 4 by 2, that is 2. So 22 plus 2, that is 24. So force into distance, that is 1102.32 is kilonewton into meter moment. And for the top down, the CG will be 4 plus 2 plus 20, that is 20 plus 6, 26, and half of 1, 26.5 will be the CG distance, and the force will be 5.78. So force into distance will give me moment. So after that I will write down total force, wind force, and total wind movement. Total wind force is coming out as 153.72 and total moment is coming out as 2445.65 kilonewton into meter. So that's it in this chapter. This chapter ends here. Thank you.